In quantum dynamics, you have seen till now two pictures. First one was Schrödinger picture and the second one was Heisenberg picture. We have seen that in Schrödinger picture, the state vector is time dependent, while the operator corresponding to an observable is independent of time. But in case of Heisenberg picture, the situation was just opposite. You have seen that in this picture, actually the state vector was time independent, but the operator was time dependent. Now in the interaction picture, you will find that in this case actually both the state vector psi and the operator a hat are time dependent. And since in this interaction picture the state vector psi and the operator a hat both are time dependent, so here the advantages of Heisenberg and Schrödinger pictures are sought to be combined. It is obvious. As the name says that this picture is interaction picture. Interaction means when your system is in an external field and the system gets interacted with the field, then this idea is utilized. And this is a common problem of quantum mechanics in general. Generally, you find that your system is in some external field. And so this picture has a very vast application. You will find its application when you will discuss the time-dependent perturbation theory, where our system is in an external field. In fact, it is seen that this approach is very useful when the Hamiltonian can be split up into two parts. The first part is independent of time and the other part is time dependent. And this situation is actually found when our system is an external field, as I have told you earlier. In fact, the time independent part of the Hamiltonian of the system is in the absence of the perturbing field or the external field, and the time dependent part arises due to the presence of the field. And so the time independent part would represent the Hamiltonian in case of when our system is in fact not in the external field. As I have told you that in this case Hamiltonian may be split into two parts. First one is time independent and another is time dependent. So let us consider that our Hamiltonian for the system h hat of t is written as h hat of 0 plus h hat 1 of t. In fact, here h hat of 0 is independent of time, or you may call it unperturbed Hamiltonian. And this h1 of t, this is dependent on time, and this part of Hamiltonian is known as perturbed Hamiltonian, or this is due to the interaction with the external field of the system. Now let us consider that this psi of t is the state vector in the Schrödinger picture, and a hat denotes the operator in the Schrödinger picture. And in interaction picture, we denote these two things by these symbols. Psi I of t, this denote actually the state vector in the interaction picture, and a hat I of t, the operator in the interaction picture. Now, first of all, we will write the expression for the time development operator in the absence of the Hamiltonian h hat 1 of t. It means when our system is not in an external field or the system is unperturbed, then what will be actually the time development operator? First of all, we will define it, and already this definition you have seen earlier while discussing the Schrödinger picture. and after that you will see how the equation of motion in this interaction picture we can find. One thing I would like to share with you, that in this lecture I will write the expression for equation of motion somewhat directly, because all the mathematical calculations I have already discussed in the earlier lectures. So you can think that this is just a homework for you. I will give just an insight and write the expression directly, but I will suggest you go through the rigorous calculation and try to obtain that result. Then your concept will be clear. And for getting the help how you can get that proper result, you may watch the previous videos again and again, and then you will have definitely an idea how to obtain that result. So here I am not going to calculate the equation of motion in a rigorous manner by solving all the steps of the problem, but I will drop some of the steps and write the expression directly, because all these things I have already discussed earlier, so this will be just a repetition. And so I hope you don't like the repetition and try yourself. When you will try yourself, you will do it, then your concept will be more clear. So I will suggest you wherever I left some of the steps, you should try yourself in your notebook. So now let us first of all define the time development operator in the absence of the perturbing Hamiltonian, that is h1 of t. So the time, this definition you have already seen in the earlier lecture. The time development operator in the absence of Hamiltonian h hat 1 of t is given by, you have seen this thing in the case of Schrodinger picture, and we denote this time development operator by the symbol u hat naught of t comma t naught. And you know, you have defined this thing earlier like this. This is e raised to the power minus I over h bar h hat 0 times t minus t naught. You have seen this definition earlier in the Schrodinger picture. And let us say this is your equation 1. So this is the time development operator in absence of this time dependent part of the Hamiltonian. You can see this h hat 0, this is time independent part of the Hamiltonian. Now first of all we will define the state vector and the operator in this interaction picture in terms of the state vector and operator in the Schrodinger picture, as we have done in case of Heisenberg picture 2. So you can say the state vector psi I of t. This is state vector psi of t in interaction picture. As you have considered it here, you can see this is your state vector in Schrodinger in interaction picture. So the state vector psi of t in the interaction picture is defined by this is defined like this: psi I of t is equal to u hat inverse 0 t naught psi of t. You know this psi of t is what? This is actually the state vector in Schrodinger picture. And when you will operate this operator on this state vector in Schrodinger picture, you will get the state vector in interaction picture. Or equivalently, you may write this as u hat star. This is actually the Hermitian adjoint of u naught hat. U naught star t of t naught psi of t. But as you can see, we have defined the time development operator u naught hat in this equation 1. But here there is actually its Hermitian adjoint. So what will be this? You can see we will simply take the complex conjugate of this operator u naught hat. And its complex conjugate will be what? You can easily say this will be e raised to the power plus I by h bar. In fact, in this definition, there is minus I by h bar. And when you will take its complex conjugate, this will be plus I by h bar. And other things will remain same. H hat naught times t minus t naught psi of t. And this is just the state vector defined in the interaction picture. So this is psi I of t. Now we will also define the operator in the interaction picture in terms of the operator in Schrodinger picture. So again you can see this a hat I of t. How this is defined? You have also seen this definition earlier in the Schrodinger picture. This can be defined as u naught hat inverse t comma t naught a hat. This a hat is the operator in Schrodinger picture. U naught hat t comma t naught. Now again, from the definition of this time development operator, you can write here the expression for these two operators, and this will be what? This is e raised to the power I over h bar h hat naught times t minus t naught. This is the expression for this u naught hat inverse, and then there will be a hat, and again we will write the expression for this u naught hat, and this is what? This is e raised to the power minus I by h bar. You know, this is h hat naught times t minus t naught. Now you can say this is your equation number 3. This is equation 3. So in this way you can see we have defined the operator in interaction picture in terms of the operator in Schrodinger picture, and also the state vector psi I of t in interaction picture in terms of the state vector psi t in Schrodinger picture. Now in Schrodinger picture, you know the equation of motion is nothing. This is simply the Schrodinger time dependent equation. So if you write the equation of motion in Schrodinger picture, you should write the time dependent equation of Schrodinger. And so what will be that? So in Schrodinger picture. In Schrodinger picture, we have, IH bar del psi by del t. Psi is actually the state vector in Schrodinger picture, and this is equal to h hat of t times operated on psi of t. Now you have seen in the equation number 1 that in this case this Hamiltonian h hat of t is actually the sum of two Hamiltonians, that is the time independent Hamiltonian h hat 0 and time dependent Hamiltonian h hat 1 of t. So let us substitute for h hat of t from this equation 1 in this result. So we can write, instead of h hat of t, we must write h hat 0 plus h hat 1 of t. This is instead of this h hat of t, and psi t, and say this is your equation number 4. And in terms of the operator, you may write that this dA hat by dt is equal to del A hat by del t. This is equation 4b. Let us say these are actually the equation of motion in the Schrodinger picture. Now from the equation you can see here the definition of this psi of t, which has been defined in this equation 2. So by using this equation 2 and the equation which I have defined here in equation 4, you can now write the equation of motion in terms of the state vector in interaction picture. So by the use of equation use of equation 3. And this is actually not equation 3 but equation 2. Sorry, one thing here I have mistaken. This should be equation number 2 and this should be 3, because I have already considered equation 1 earlier. And so you should write here 4 and this will be 5 and this is, let us say this is 4a and this is 4b, let us say. And by the use of this equation 3 which I have defined here and the equation defined here in this equation 4a, 3 and 4a, the equation of motion in the interaction picture in terms of the state vector state vector is given as, you can write I h bar del psi I by del t. Instead of psi, now we write psi I, and this will be equal to hi1 psi I of t, psi I of t, and say this is your equation 5. Actually here you know this operator hi hat of 1, this is defined on the basis of this definition. As you can see, ai hat has been defined like this in this equation 4. So in the light of this equation 4, you can define this operator hi hat of 1 like this. This is u naught hat inverse t comma t naught h hat 1. This is actually the Hamiltonian in case of the Schrodinger picture, and u naught hat of t comma t naught, t comma t naught. Say this is 5a. So this equation 5 is actually the equation of motion in the interaction picture in terms of the state vector, and you can see that actually this equation is just like the equation of motion for a state vector in the Schrodinger picture. So you can say that the state vector in the interaction picture is determined by the Schrodinger equation. Thus, the state vector in interaction picture is determined by Schrodinger equation. Now, by the use of equation defined in here, you can see this equation which we have defined actually in the equation here. Sorry, yes, this equation again 3 and not 3 but equation 4. Equation 4, because I want to now write the equation of motion in terms of the operator. So see this equation 4, and in the light of this equation 4 and this equation 4b, you can write the equation of motion in terms of this operator ai hat in this interaction picture, and the result will be exactly same as that in case of the Heisenberg picture. And as I have told you that I am not going to follow all of the steps, I will write direct the expression and you should try it to obtain the result. So again, equation of motion in terms of the operator when the operator is an explicit function of time. explicit function of time. In the light of previous result you have seen earlier in the two pictures, you can write this equation of motion like this: ai hat dai hat by dt. This is equal to del ai hat by del t plus 1 over I h bar times commutator bracket of ai hat with hi hat 0. Hi hat 0. And say this is your equation 6. In fact, this is the equation of motion in terms of the operator. In fact, you know here this operator hi hat 0, this is defined like this: u naught hat inverse t comma t naught h hat 0 and u hat naught t comma t naught. Actually, this is the time independent part of the Hamiltonian in interaction picture, and this h hat naught is actually the time independent part of Hamiltonian in the Schrodinger picture. And this is just the definition. In the light of this equation, you can see here I have written that equation. So this is your equation of motion in interaction picture in terms of the operator. And here you can see that actually in the interaction picture the equation of motion in terms of operator is just like the equation of motion in Heisenberg picture. So here you can say that the Hamiltonian hi of 0 or h hat 0, you can say, actually comes in this equation of motion. So this is just identical to the Hamiltonian of the Heisenberg picture. Now, after getting these two equations of motion, we can also find the equation of motion for the expectation value of the operator. So I will again write the expression directly. You should try to obtain it. So the equation of motion for the expectation value of the operator ai hat is given as, in fact in this case we will write d dt expectation value of ai hat, and you know this will be del expectation value of del ai hat by del t and plus expectation value of 1 over I h bar times commutator bracket of ai hat and hi hat 0. This is actually the equation of motion in terms of expectation value of the operator. And here you know this Hamiltonian h hat I is equal to what? This is hi hat 0 plus hi hat 1. So these are the equations of motion in case of interaction picture. As I have told you that this interaction picture finds its application when your system is in an external field, and we will see such situations more rigorously or more vividly when we will discuss actually the theory of time dependent perturbation, and so this basic fundamental will be used there.